Hello students, good morning. Today we are going to see the continuation for the coordination compound. So that is the color of the complex in the crystal field splitting. So first we are going to see the what is meant by color of the complex. So everyone know that a substance exhibit color when it absorb the light. Suppose so we are seeing any of the object means we can easily recognize it is the what color. So that is what happen in our mind. So that is in our eyes, the transmitted light enters our eyes, our brain recognizes that color. Okay, so this is the basic things. First one is a substance exhibit a color when it absorb light at a particular wavelength and transmit the rest of the visible light. So that is the reason we can easily visible the particular light. So that another one is the color of the transmitted light is given by the complementary color of the absorbed light. So how it will absorb, how it will explain in the coordination compound, because in our lab, so everyone seeing the color complex, right? So that is the potassium dichromate. So when you are seeing that potassium dichromate, that is K2Cr2O7. So here that is Cr is the D block element. So that is the metal, chromium metal. So that is KMnO4. The potassium permanganate, that is purple in color. So the manganese, this is also metal, that is the D block element. So in our lab, all the color complex are present in the D block elements metal. So that is main important things, that all the D block elements are involved in the colored complex. What is the reason? The D block element absorbs some light in the particular wavelength and transmitted that light in a particular another wavelength. How it will explain? One easy way it can explain that. So first one is, so what are the color? What are the 7 color? That is VIBGR, right? VI, VIBG, VIBGR. Okay, that is the color VIBGR. So I am how to write? I am here writing first violet and indigo. I am writing the same thing. Again, next one is blue. Then again another one is green. Then another one is yellow. Right? Another one is orange. Right? Then again red. Okay, so this is I am writing the seven colors, right? So how it will explain that? Suppose we are observing the light, we are observing visible violet and indigo, means it is reflect only the yellow color. So again it will reflected, suppose orange color, the red color is observed, mean it is reflected the green color. Suppose blue color is observed, means it will reflected the orange color. Suppose orange color is observed, means it is reflected the blue color. So that is the wavelength they are given, violet and indigo, that is the wavelength is 400 to 450 nanometer, right? So that is, then blue color is 450 to 1000, that is 450 to 480, right? The green color is also 480 to 560, 480 to 560 nanometer. This is yellow is 560 to 600 nanometer. So this is red is transmitted 640 to 700 nanometer. So this is the light absorbing that color. So first one is, so the VIBGR, so what color is observed? So that is VIBGR, violet and indigo is observed color, means it is transmitted the yellow color. Red color observed means it is transmitted green color. So that is the easy way to remember that this is the color wheel of the complementary colors. This is the complementary colors of this 7 colors. So here one wavelength, particular wavelength is here in your textbook. So this is one tabular column. What are this? The wavelength of this absorbed light. What wavelength? Wavelength in the absorbed light in the centimeter per centimeter. The color of the absorbed light is violet color. So violet color observed means that observed color means that is transmitted color, right? So that is yellow color. This is blue color means transmitted orange, green, red. So we can easily remember what is the way to remember that color means. First we are writing here. You are writing, leave it to the indigo. So that is violet, blue, green, yellow, orange, red. Okay, so this is the observed color, the wavelength. So here the it is observed means first you are writing the 3 color in the order. So that is YOR. Then again VBG. So that is violet, blue and green. Okay, so this is the order, you remember that. So this is the way easily remember the color compound in that color wheel of this complementary colors. Okay, so it will, how it will observe in the coordination compound. So that is the observed color of the coordination compound using the crystal field splitting theory. So we learned already the d orbitals are, what are the two splittings observed in the d orbital? What are the two splitting is observed in the d orbitals? D orbital, that is the crystal field theory. So that is the d orbital, right? It is observed in the, okay, so it is observed the two energy level. So that is in the octahedral compound, that is T2G, that is 3 boxes T2G, here EG, right? So that is the 2 boxes here, that is EG. Okay, T2G and the EG. When the white light falls on the complex, the central metal absorbs the visible light. So when the central metal atom is absorbs the light, mean d orbital. When the central metal atom is absorbs the light, what will happen? It is go to the excited state. It is returned the crystal field splitting, the transmitted rest of the light, which is responsible for the color of the complex. So it will absorb the sunlight and go to the excited state, and return to the excited state, it will emit the rays. Okay, so that is called as DD transition. How it will explain mean, that is the, let us understand the another one is titanium molecules, the titanium compound, complex compound, titanium H2O 6 3+. Okay, this is the compound. What is the titanium 3+? What is the electronic configuration? Is titanium 3+ is D1 configuration, right? So D1 configuration, so that is the T2G. T2G means that is 3 boxes are there. So D1 orbital, that is only 1 electron here, right? It is go to the EG level, excited state. So that is EG, excited state, what will happen? It is goes absorb some amount of energy and go to the excited state, that is dx square minus y square dz square, right? So here that is dxy, dyz, dzx. Okay, so it is written to that, that is the, again it is written to that original level. So release some amount of energy. The energy difference in the octahedral is, so that is 239.7 kilojoule mole minus 1. Okay, so this is the way it is explained in the observed light and promotes the itself. Suppose some amount of energy observed, it is go to the excited state. So it is returned to the original state, it will emit the energy. So that is called as DD transition. So the this absorption is called as DD transition. So that is, it is due to the difference in the magnitude of the crystal field splitting by this ligand. So that is because of this ligand only, it will absorb this light, it is go to the excited state, it will return to the original state, it is emitted that light. Okay, so this is in your textbook, it will show this color. This is the diagram. So dxy, dyz, dzx. So this is the way. So they are explained, that is the D1, that is only 1 electron is here. It is go to the excited state, it is returned to the original state. It will release the amount of energy. The difference is, that is 239.7 kilojoule. That is called as DD transition. Okay, so next we are going to see the metallic carbonyls. So next one is metallic carbonyls. What is mean by metallic carbonyls? The metal carbonyls are the transition metal complex of the carbon monoxide. So that is carbon monoxide. It is bond between the metal and carbon bond. So in this complex, CO molecule is act as a neutral ligand. So that is CO is a neutral ligand, right? So this is the neutral ligand. So the neutral ligand, so that is homoleptic compound. Homoleptic compound, that is the same ligand. So that is homoleptic compound. So what is the compound name? Nickel tetracarbonyl. Nickel tetracarbonyl compound. Nickel tetracarbonyl compound. So these metallic carbonyls are, so according to the industrial importance, that is mainly it is used for the catalytic properties. So generally the metal carbonyl is classified into 2 different ways. First one is classification based on the number of metal atoms. So 2 way, based on number of metal atom, and the second one is classification based on the structure. Second is classification based on the structure. First we are going to see the classification based on the number of metal atom. First, how it will explain that. First one is depending upon the number of metal atom present in the metallic carbonyl compound, it is classified. First one is mononuclear carbonyls. Mononuclear carbonyl. Say example. So that is nickel. Mononuclear based on the number of metal atoms. So here that is only one metal atom is here. So that is called as mononuclear carbonyl. Nickel tetracarbonyl. Again FeCO5 pentacarbonyl. Iron pentacarbonyl. Okay, so next one is number of metal atom. More than two or more metals are called polynuclear carbonyls. Polynuclear carbonyls. What is polynuclear carbonyls? More than two, right? So that is CO2, CO8. CO2, CO8. Okay, that is the homonuclear. So polynuclear hetero compound. So that is again Mn2 CO10, right? Again, so that is heteronuclear. So that is what is meant by heteronuclear. Two different metal atom, Mn, CO, then CO9, right? So that is two different, that is heteronuclear atom. So this is the classification based on the number of metal atom. So next one is based on the structure. So how it will be classified? First one is that is referred as the terminal attached only one metal atom. So the structure of binuclear metal carbonyl involve a metal-metal bond or the bridging CO bond. So based on the structure, how it will classify? So terminal carbonyl groups are the bridge carbonyls. First one is terminal carbonyl compound, terminal carbonyl or bridging carbonyl. What is meant by terminal carbonyl? So first one is non-bridged metal carbonyl. So what is meant by non-bridged metal carbonyl? Example, non-bridged metal carbonyl. Non-bridged metal carbonyl. First one is NiCO4. Okay, so that is non-bridged metal carbonyl. So here that is nickel. Here CO. So here also CO. That is the non-metal. This is non-bridged metal carbonyl. Okay, so non-bridged metal carbonyl with contain terminal carbonyl. So terminal carbonyl means the carbonyl compound present at the terminal. So that is called as terminal carbonyl. The structure Mn2 actually involve a metal-metal bond. So is correctly represented as CO5 Mn. So next one is another one is bridged metal carbonyl. This is one example, non-bridged metal carbonyl. Next one is this is terminal carbonyl. Next one is metal-metal bond. Example is Mn2 CO10, right? So this is the Mn2. So how it will be? Draw this one. This is Mn. Here also Mn. CO. Here the metal, say metal bonded. So here only the carbonyl present at the terminal, but here metal bonded. So this is called as bridged metal carbonyl. So that is metal carbonyl compound. Okay, so this is the another one. So this is called as metal carbonyl. The bond distance is, so what is the bond distance? That is 2.79 Armstrong. So this is the non-bridge metal carbonyl. First one is terminal and the another one is metal-metal bond. Next one is bridged carbonyl. What is meant by bridged carbonyl? First one is bridged carbonyl. So what is meant by bridged carbonyl? So first one is example Fe2CO9. Okay, so this is the example of bridged carbonyl. So how it will be explained that? So here that is Fe. So here that is CO bond is bridged between the two metal atom, right? CO okay, so this is the bridged metal carbonyl. Di-ion nanocarbonyl molecule consists of 3 bridging CO. So here one CO, here one CO. This is 3 bridging CO, 6 terminal carbonyl. Here 3, that is the terminal. Terminal means what is meant by terminal? So end la carbonyl irunda, that is called as terminal. Idu vandu bridge la irukku. So that is in between the two metals. So that is the bridged carbonyl. And another one example. 2 isomers are possible. Dicobalto tetracarbonyl. That is another one is CO2 CO8. So that is cobalt. So here CO, here also CO, here also CO. This is cobalt, this is carbonyl. Okay, so this is the another one example. So next we are going to see the bonding in the metal carbonyl. What is meant by bonding in the metal carbonyl? Based on the number of metal atom, based on the structure. So bonding of this metal carbonyl. Next we are going to see the bonding of the metal carbonyl. Bonding of the metal carbonyl. So that is the carbonyl ligand consists of 2 components. First one is that is sigma and the pi bond. So sigma character and the pi character, pi bond character. So how it will can be explained? So based on the metallic bond, so how it will occur, that is metal carbonyl. So how it will metal bond is obtained means, so the carbonyl is ligand is donated the 2 electron to the metal to making a bond formation. So that is the carbonyl and metal ligand. So here that is 2 bond is present here, that is sigma bond and another one is pi bond. So how it will be explained that? So here that is 2 types of bond will be explained. So here metal and carbon and oxygen, right? So the metal is the linear overlap. So linear overlap is forming a linear overlap forming a sigma bond, right? So another one is pi bond. How it will be pi bond form? So that is the carbonyl, oxygen will be formed the pi bond. So this is we are studied in the that is the molecular orbital theory, how it will sigma bond, how it will formed in the pi bond, right? So here that is the same thing. So in your textbook, that is sigma bond, pi bond, how it will be formed. So that is here, that is the metal carbonyl. So carbonyl, this is the pi bond will be formed, that is the axial overlap, that is pi bond will be formed. This is the pi back bond, this is the pi forward bond. So that is metal donated to the, so the oxygen donated 2 electron to forming the metal. So that is forward bond. The same metal, so the carbon is donated 2 electrons. So the metal is donated 2 electron to the carbonyl compound, that is pi back bond. So so this is the another one metallic bond formation. So next we are going to see the stability of the metal complexes. Next one is stability of metal complex. Okay, the stability of metal complex in the coordination compound interpreted in the two different ways. So first one is thermodynamic stability. Thermodynamic stability. Thermodynamic stability. And another one is kinetic stability. So what is meant by thermodynamic stability? Mainly it is change in the delta G. So that is the free energy change. So kinetic stability can be explained the ligand substitution. So that is how much of ligand substitute with the central metal atom. That is the substitution of this ligand to the central metal atom. So it can be measured using that is stability constant. So what is the stability constant? That is beta. So the stability constant beta can be used to measure the substitution, that is kinetic stability. So that is first one is the ligand substitution takes place in a very rapid. So that is the kinetic stability of the coordination compound. According to the ligand substitution only we can calculate it. First one is the ligand substitution takes place undergo rapid ligand substitution. So the ligand undergoes the rapid substitution means that is called as labile complex. Labile complex. The complex name is called as labile complex. Suppose the ligand substitution takes place in a very slow manner. So that is very slow means that is called as very slowly means that is called as no substitution takes place. That complex is called as inert complexes. Okay, it can be classified two complexes. First one is labile complex and the inert complex. What is labile complex? It takes place in a rapid substitution of this ligand, that is called as labile complex. It is very slowly. Ligand substitution takes place very slowly. It is called as inert complexes. Okay, so next one is, so this inert complexes, metal complex with a ligand. So how with this metal complex, when you are substituted with a ligand, how with metal complexes resistant for the substitution, that we can be measured using this the stability constant. Suppose we are attached with the ligand substitution with the central metal atom. So that is metal complex substitute with that ligand. How much of this metal complex is resist for this substitution? The resistant அப்படினா என்ன அர்த்தம்? The metal complex எப்படி வந்து அதை தடுக்குது. So that is the resistant for this substitution. That we can measure using this stability constant, that is beta. Say for example, that is one copper 2+ when react with ligand, that is ammonia, it will form this equilibrium complex. So that is copper NH3 4 and this 2+. Okay, that is charge. So that is the metal complex. So how to write this equilibrium constant? That is called as beta constant. How to write? Product concentration. So that is Cu NH3 4 2+, product concentration divided by reactant concentration Cu2+, right? Then NH3, the coefficient raised to the power of this concentration, that is 4, right? So this is the beta stability constant. So that is called as formation of equilibrium. So the beta is called as formation of equilibrium. Formation of equilibrium. So here that is greater the stability, greater the bond length. So here that is metal, it is represent metal with the ligand. Ligand is bind with that metal. So that is the strength of this bond. This is called as strength of this bond. Strength of the bond. The bond strength will be in greater mean the stability is also greater. Bond strength increases, that is dissociation decreases. Bond strength increases, that is dissociation decreases, right? So that is again, so that is dissociation will take place. The dissociation mean that is the equation will be reversed. So how to reverse? So that is Cu NH3 4 Cu2 plus, it is the reversed one. So Cu2 plus 4NH3, right? So the equation is reversed. So that is the again dissociation equilibrium. This is called as dissociation equilibrium can be measured. How to write the equilibrium constant? So that is called the dissociation, that is alpha. So how to product concentration? Cu2 plus NH3 4 divided by CuNH3 4 2 plus, right? So that is the dissociation constant. The dissociation equilibrium can be measured, that is alpha. The dissociation constant, it is otherwise called as instability constant. Instability constant. Okay, that is instability constant, that is this is alpha. The stability constant, that is beta. So what is the relation between the stability and the instability mean? That is the from 1 and 2 is the reciprocal of dissociation equilibrium. So the beta is the reciprocal of 1 by alpha. Okay, so here that is the reverse of this beta. So that is stability constant is a reciprocal of dissociation of this equilibrium. So what is the significance of this stability constant? The stability constant is a reciprocal of the dissociation of this equilibrium constant. So next one is, what is the significance of this stability constant? What are the significance of this stability constant? It is the stepwise formation of this constant. So that is the metal compound, the substitution of this metal compound. It is 6 ligand. This approaches with the 6 ligand when to form the metal complex. So that is metal with a ligand. Then substitution. So the substitution, 6th substitution takes place. So the overall, the concentration, that is beta stability concentration for overall. So that is, we can write ML6 S the power 6 divided by MS6 then L power 6. Okay, so this is the overall concentration. But here, that is overall concentration. So here the stepwise concentration, that is the overall stability constant. A solvent is present, is large in excess. So this is, we are considered as a solvent, that is, this is the S is the solvent we are considered. So this equation becomes beta overall is equal to ML6 then MS6 then L power 6. Okay, so this is the overall constant, because if the 6 ligand had added to the metal atom 1 by 1, not only the ligand is directly, it is not only 6 ligand is directly approached to the metal, means it is 1 by 1 it will be added. So how it will be added? First one is MS6 plus 1 ligand, it will form the metal complex. So that is MS5, 1 ligand will be formed. So that is solvent. So how to write the equilibrium? K1 is equal to, how to write? So that is MS5 ligand divided by MS6 plus ligand. Okay. So now what is again another ligand, MS5L plus again another ligand will be substituted. What will compound form? MS4L2 then plus S. What is K2? K2 is equal to MS4L2 divided by MS6 L, right? So this is the another one. So next one is MS4L2 then L. What is that equilibrium? Again MS3L3 plus S. What is K3? Equal to MS3L3 divided by MS6 This is MS5L. This is MS4L 2. Okay, so then again L, then again MS3L3 plus L. What is the equilibrium? MS2L4 plus S K4. What is K4? MS2L4. Here MS3L3 L, right? So here MS2L4 plus L, MS1L5. So plus S, what is K5? MSL5 divided by MS2L4 L, right? So then MSL5 plus another L, ML6. Okay, so then this is the final one, K6 equal to ML6 divided by MSL5 then L. Okay, this is in the above equilibrium values are called the stepwise. This is called as the K1, K2, K3. That are called as K1, K2, K3, K4, K5, K6 are the stepwise stability constant. Stepwise stability constant. Stepwise stability constant. Okay, so then beta, what is beta? Beta equal to K1, K2, K3, K4, K5, K6. And taking logarithm of both sides, so log beta equal to log of K1 plus log of K2 plus log of K3 plus log of K4 plus log of K5 plus log of K6. Okay, according to this one, we can easily calculate the stepwise stability constant of this one. Okay, next one, this lesson, the last topic is what are the importance of this application of the coordination complex. What are the main complex coordination complex? First one is, so the coordination complexes are many importance, plants, animals and the minerals. What are the application of this coordination compound? First one is phthalo blue. A blue pigment is a complex copper to iron and the printing ink and the packaging industry. The phthalo blue is a blue color pigment using for the printing ink and the packing industry. Another one is purification of nickel. So that is the involves the formation of nickel tetracarbonyl compound. The pure nickel is the decomposition. It is used in the purification of the Mons process. And another one is chelating agents. What is meant by chelating agent? That is called as coagulation process. So வந்து blood வந்து coagulate ஆகாம தடுக்கிறது. So that is called as chelating agent, CDTA. So what is chelating agent? So in the suppose for any blood testing, suppose taking the blood means inside the test tube, the chelating agent CDTA present inside the test tube. So that is to prevent the coagulation of this blood. So that is lanthanide water and also removing the lead poisoning. So the chelating EDTA is also used to remove the lead poisoning. Another one is coordination complex is extraction of silver and gold complex, cyano complex. So that is the MacArthur forest. In the D block elements we studied the purification of gold and silver using the MacArthur forest cyanide process. In this process the coordination complex are also used in the extraction of gold and silver. And another one is some metal ions are estimated more accurately by complex formation. In the nickel chloride solution is estimated accurately the complex called. So that is the metal ions are complex formation estimated the accurately for the forming of the complex. Example DMG, dimethyl glyoximate, that is two molecule of dimethyl glyoximate. Okay, so this is another one is many other complexes catalyst. So many other coordination complex in the inorganic reaction, that is Wilkinson catalyst, that is phosphorus trichloride and the rhodium chloride. At the Ziegler-Natta catalyst, we have studied in the D block element titanium tetrachloride and the aluminum tetraethyl. So triethyl. So that is the another one. So next one is, in order to get the fine uniform deposit of superior metal, coordination complexes are used to electrolytic path. So that is the formation of this complex compound. Electrolytic metal is also used in the water electrolytic path. Another one is, many complexes are used in the medicine. So that is calcium EDTA. The chelate is the treatment of lead and radioactive poisoning, removing lead and the radioactive metals from the body. So suppose this calcium EDTA chelate, so this one for used in the continuously, they are used in the X-ray lab. They are very frequently exposed to the X-ray rays, means they are in the body containing some lead poisoning. So to remove that lead poisoning, they are using the calcium EDTA chelate. And another one is, cisplatin is used in the anti-tumor drug of the cancer treatment. So in the cancer treatment, cisplatin is used in the anti-tumor drug. So this is the another one. So another one is, in photography, for the film developing the decomposed silver bromide for the shiny film coating, that is silver bromide is a complex compound. It is used in the sodium dithiosulfato-argentate, which can be easily removed by washing the water, ordinary water. So this is the another one. So next one is, that is the sodium silver bromide, sodium thiosulfate, sodium silver thiosulfate and the sodium bromide. Okay, apart from this, external that is used in the biological system. So many biological system containing the metal complexes. Say for example, RBC, red blood corpuscles are composed the heme group, which is Fe2+, that is porphyrin complex. We already know that in the red blood cells, that is RBC. So that is mainly the blood cell containing iron and also the side group containing porphyrin. Another one is chlorophyll. The chlorophyll also containing, in the structure of chlorophyll, in the center of the metal atom, this magnesium. So the another one is played an important role in the photosynthesis, in which the plants can water can the carbohydrate and oxygen. During the photosynthesis, the magnesium metal can be used in the chlorophyll pigment. And another one is vitamin B12, cyanocobalamin. So vitamin B12 is also vitamin, consists of the central metal atom. CO is surrounded by the porphyrin. This is the another one, vitamin B12. Another one is, many enzymes are known as metal complexes, carboxypeptidase and protease enzyme, hydrolytic enzyme. So digestion contains zinc ion, coordinated is the protein. So another one is carboxypeptidase. Then so many enzymes are the complex compound. These are also used in the coordination compound. So this is the another one is cisplatin. So that is, I already told, that is used in the anti-tumor drugs. Okay. So what is the main action of this cisplatin? What is the structure of? It is a square planar coordination compound, that is similar ligands are adjacent positions. That is, similar ligands are present in the adjacent positions. So here that is ammonia and the ligand. So that is the similar ligands are, these are the cisplatin based anti-cancer drugs. That drugs undergo hydrolysis and react with DNA to produce various crosslinks. These crosslinks hinder the DNA replication. So what is the main purpose of this cisplatin? It is react with the DNA and to produce various crosslinks, and also that is prevent the growth of this DNA replication. That is the another one. This is the cis-calls protein. This is called cellular protein, inhibit the mitosis. So mainly it is prevent the cell division. So this is the, that's all about the important applications of this coordination compound. Okay, we completed the 5th lesson. Next we are going to see the 2nd volume. Okay, see you tomorrow, the 2nd volume. Okay, thank you children.